Welcome mathematicians, and today we're looking at the MAT 2017 question 2, and I'm going to try and record it on PowerPoint, which I haven't done before. So let's get on with it. So it's given that there is a unique real number alpha that satisfies the equation alpha cubed plus alpha squared equals 1, and we're not asked to prove it, and we're told that we should be looking for a solution in the domain between 0 and 1 for alpha. Okay, so let's get on with that. What I'd recommend is that you turn that question into a function, and you can see from my solution I turn it into a function of alpha is equal to alpha cubed plus alpha squared minus 1, and I'm going to look for a value of alpha where that must equal 0. And of course, if I put either extreme ends of my domain, namely 0 and 1, into my function, I can see I get minus 1 and 1. So there's a change in sign. This is a continuous function, so hence there must be a solution for alpha between the values of 0 and 1. And of course that leaves us with the next part, which says show that alpha to the power of 4 is equal to minus 1 plus alpha squared. Well, again, not so bad. The reason it's not so bad is that if alpha cubed plus alpha squared equals 1, then we can multiply through by alpha and replace the alpha cubed with what alpha cubed is equal to, namely 1 minus alpha squared. And if we do that, it tidies up nicely to alpha to the power of 4 is equal to alpha squared plus alpha minus 1 as required. So now that we've disposed of the early 4 marks, which are not so bad, get to the meat of the question, we're actually given something which is a bit tricky. 4 functions of alpha we have to find. They want quadratic polynomials, and they want it in the order where we get the coefficients of the alpha squared is the c value and not the a value. A little bit peculiar. Right, and we're asked to find an expression in terms of a quadratic expression for alpha, the inverse of alpha under 1. So how do we go about this? Well, if we consider that we've been given alpha cubed plus alpha squared equals 1, if I divide everything through by alpha, I get an expression for 1 over alpha. And if you do so, I'll find you find a nice simple answer that 1 over alpha is equal to alpha plus alpha squared. So that means that a is equal to 0, b is equal to 1, c is equal to 1 in the first part of this third part of the question. Next, we're given an infinite sum to evaluate. 1 minus alpha plus alpha squared minus alpha cubed plus alpha to the power of 4 minus alpha to the power of 5. Well, that certainly looks like a geometric series to me. Looks like the first term, a, is equal to 1, and the common ratio looks like it's minus alpha, doesn't it? Well, if we've got the first term and the common ratio, we can use the expression for summing, the formula for summing to infinity, which we all know is alpha over a over 1 minus r, and that will give us a sum of 1 over 1 plus a. But unfortunately, that's not quite the format they want, so we've got to think of a clever way of turning that into a quadratic. And the thing to do, I think, there is look at the numerator equals 1, but we know that 1 is the same as alpha cubed plus alpha squared. So if we put that on top, we've got a division to do the division, and it comes out extraordinarily nicely, just a alpha squared. So a is equal to 0, b is equal to 0, and c is equal to 1. And the next part, part C, looks deceptively easy. It's 1 over 1 minus alpha. Now, the only thing I can think of immediately looking up on that is it does look suspiciously like the summation of an infinite geometric series. So we could be able to work that out, I think. So starting on the premise that our summation, s, is equal to 1 over 1 minus a, we can try the same tack of getting rid of that numerator 1 and replacing it with alpha cubed plus alpha squared. And I've tied it up a little bit. I've changed the denominator to alpha minus 1 simply because I find that easier to do long divisions like that. So I'm going to divide minus alpha cubed minus alpha squared by alpha minus 1. If I do so, you get the first 3 terms pop out nicely, minus alpha squared minus 2 alpha minus 2. And of course you're left with a remainder of minus 2. And of course I'm dividing by alpha minus 1. Now if I fiddle around with that denominator, making it 1 minus alpha, the sign changes from a minus to a plus, doesn't it? Now you'll notice that at the end of that line I've got s is equal to minus alpha squared minus 2 alpha minus 2 plus 2 lots of s. If I take the s's onto one side, I'm going to get minus s is equal to minus alpha squared minus 2a minus 2, and that ties us up to alpha squared plus 2 alpha plus 2, which means that a is equal to 2, b is equal to 2, and c is equal to 1. Now I have to admit that when I looked at the last part, the infinite product, so rather than a big Greek sigma for summation, we've got a big Greek pi for product. I thought that's a disaster, because we don't do that in A level or further maths A level, and it's a long time since I've mucked around with infinite products, but it wasn't quite as bad as it initially seems. So after a little bit of scratching of the head, I thought I'm just going to multiply out a few of these brackets, see what happens, and of course once I did that, spotted a very nice pattern. It just becomes 1 plus a squared plus a cubed plus a to the power of 4, etc., etc. I used ellipsis there. You can see my solution from Newton's notation. Right, so this question really is the same as a geometric series summation, and that's 1 over 1 minus a. We've already done that in part C, so the answer is a is equal to 2, b is equal to 2, and c is equal to 1. Thank you very much.